we have a few terms that we need to make sure everybody's clear on what they mean. First one, a sequence. When we talk about sequence, we're talking about an ordered list of numbers. What do we mean when we say ordered? Well, there is generally a pattern. So, for example, 1, 2, 3, 4, 5, there's an order to that. And you could probably continue it. 6, 7, 8, 9, 10. If I said 5, 25, 125, 625, is there a pattern to it? Yes, there's a specific order associated with it. That's when we say ordered. There is a certain direction they're going. So if I said 1, 3, 2, 4, 5, it's not really ordered. And a couple more. An explicit formula. It's something that an is a function of n. And note, we use a sub n as generally the function for a sequence or a series. For a series. Yeah, sequence. So you would see something like this. an equals, I don't know, 5n plus 3. And we could use this and say, what is the first term of the sequence? Well, a1 would equal what? 8. And how do you get that? Yeah, we say if n is 1, we do 5 times 1 plus 3. So what would a4 be? What? Okay, 23. 5 times 4 plus 3. So this, when we see an explicit formula or ask for an explicit formula, it's a formula where I can say for the fifth term, I can plug in 5 for n, and it tells me what the fifth term is. We also have recursive formulas. This one is an is dependent on previous term. In other words, we might start with something like this, where it says a1 equals 3, an equals 2 times an minus 1 plus n. So first, what's a1? It says 2 times an minus 1 plus n. So what's a1? 3. What is a2? Well, if we're looking at a2, what is n? 2. So we're going to have to plug in 2 for all the n. So in here, we're going to say 2 minus 1 is 1. So we're going to have 2 times a1 plus, what is n? 2. So yeah, so what is a1 equal to? 3. So we're going to have a2 equals 2 times 3 plus 2. So what if I wanted a5? What is what's this? Right there? Yeah, n minus 1. What if I wanted a5? What would I do? Yeah, a5 would be equal to 2 times a4 plus 2. Do I know what a4 is? No, so I'd have to get a4, what do I have to do? Figure out a3. To get a3, what do I have to know? a2, and so on. So when we look at a recursive definition, each one builds on itself. You have to get a1 before you can get a2, and you have to get a2 before you get a3, and so on. And so, if you were looking for A100 in this case, it might be a bit tricky, or it might take a bit of time. Unless you actually got the pattern. So you got the pattern to go with it. So these are two different ways of describing something. Here we've got an explicit formula and a recursive formula. I'll tell you the recursive formula can do things that the explicit formula can't. Like, anybody heard of Fibonacci? Yes. What is the Fibonacci sequence? Okay. There are some fractals that are based on it. So it starts with A1 equals 1. A2 equals 1. AN is equal to AN minus 1 plus AN minus 2. So your first term is 1, second term is 1. What would your third term be? If we're looking at A3, we plug in 3 here. 3 minus 1 is 2, so we want A2 plus, plug in 3 here. 3 minus 2 is 1, so A2 plus A1, which is 2. Now if I wanted A4, what am I going to do? Well, plug in 4 here. 4 minus 1 is? We have A3 plus A2. 2 plus 1, 3. What about A5? 5. Then the next one, A6. Gives us 8. Then we get 13, 21, 34, and so on. Are you seeing where these are coming from? So each one of them we're adding the 2 previous, like these 2 to get that one. These 2 to get that one, and so on. These 2 to get that one. Now, it might be possible to do this with an explicit formula in this form. However, if it is, it's going to be much, much more complicated than this. It would be a very complicated formula. Whereas with the recursive formula, it is very simple thing to do. So there are some advantages to having a recursive formula, even though, if I was looking for the 23rd term of this, it would be a bit of a mess to get there, but eventually you could get there. So, what is the difference between something that's convergent and divergent? Yeah, converge, coming together, divergent would be going apart. So when we're talking about sequences, convergent means approaching a value. And this would be not approaching a value. But not doing so. No example of something that's a convergent sequence. Actually, I'll just do a sequence and see. Is it convergent or divergent? AN equals 2 to the n minus 1. So if I plug in 2, what am I going to get? Three. If I plug in 2, 2 squared is 4 minus 1, 3. If I plug in 5, what am I going to get? 2 to the 5th is 32 minus 1, 31. If I just keep plugging bigger and bigger in, is it going to a certain value or just growing? Okay, so this one would be divergent. So, because it's not ever approaching a certain value. AN equals the 2 over 3n. How's this one? Okay. If I plug in 5, I get 2 over 15. If I plug in 20, it would be 2 over 60. What number is it converging to? 0 in the long run. So this one, if I plug in bigger and bigger n, eventually it's getting closer and closer to 0. So we can say the limit as it goes to infinity is 0. So this one is convergent. Everybody with me so far? Okay. Now, another term, a series. So a series, when we talk about a series, it is the sum of the terms of a sequence. What does sum mean? Yeah, adding. So we're adding all the terms of a sequence. So we're adding the terms of a sequence. So if I did, let's see, an equals 5n plus 3. Okay, what's its first term? 8, second term. Third term. Fourth term. Now, are you just using the formula, or are you actually looking at the pattern here? What's the pattern? Adding 5. So what's the next one? 28, 33. Yeah, it is. If we continue that going down there. Now, if I want the series for this, and we're going to talk about partial sums. Okay, partial sum is adding part of the series. So when we look at the partial sum, I'm going to put that over here. What would the first partial sum be? You just have one number. What do you get? 8. Second partial sum. 8 plus 13. 21. Third partial sum. 8 plus 13 plus 18. 39. Fourth partial sum. Okay? So when you talk about the partial sum, we just add up all the numbers up to it. So this would be the first, second, third, fourth, and let's do fifth as well. Fifth partial sum, 62 plus 28. 90. Now, this kind of brings up a thing. Wouldn't it be nice if we had a way of writing? We want the fifth partial sum or the 23rd partial sum in a very compact method. And that's where we get sigma notation. So, anytime you see this symbol in mathematics, we're talking about a sum. This is a capital Greek letter, the capital sigma. And it means we're adding several things together. So if we saw this, what this means is we are starting at n equals 1. So this is our starting point. The first number we're going to plug in. K is ending point. So the K is the last number we're going to plug in. And AN is the function. So when you see this, it says we're starting with A1 plus A2 plus A3, and keep going until we get to AK. You follow that? Okay. So actually, we're going to look at some examples of this. So we're going to say the sum of n equals 1 to, let's say, 6 of 3n. Okay? So what's the first number we're going to plug in? 1. So we're going to do 3 times 1. 3 plus, plug in 2. 6 plus, plug in 3. Plus, plug in 4. Plus, plug in 5. Plus, plug in 6. Now, because we got to 6, that means we're going to stop at 6. So we plugged in every number from 1 until we got to 6. Now add them all together. So 3 plus 18 is 21, 21, 21, so 63. Okay, does that make sense what we did? Now the ones that get confusing are ones like this. Let's just say I'm going to go k equals 1 to 7 of 2. Remember, it doesn't matter what variable I use. It's just whatever variable I have down here is the number where I'm plugging in over here. So what's going to happen if I plug in 1 for all the k's in my function? What do I get? So what happens? What do I get? 2. What happens if I plug in 2? 2. What happens if I plug in 2? Or 3, I mean. 2 plus 2 plus 2, 1, 2, 3, 4, 5, 6, 7. That's base 14. So because there's no variable here in my function, I'm just adding the same number every time. Let's say if I go p equals 1 to 4 of 3 p n. What am I going to get if I plug in 1? 3n. Because I plug in 1 here, 3 times 1 times n. If I plug in 2, 6n. Plug in 3. And plug in 4. That's 12n. Add them all together, gives me 30n. Now, I'm going to give you I'm going to write out the sum. I want you to write it in sigma notation. So if I say 3 plus 7 plus 11 plus 15 what is this in sigma notation? So what do you have to recognize? Okay, what? Okay, point? Ending point, okay. So how many numbers are there? So 7. So we know we're going to let's just say n equals 1 to 7. Now what? What? Oh, function, okay. Yeah, we need to figure out what the function is. How can you do it? Good. Okay. Yeah. does this look like it's linear? Okay. Like, is it changing the same amount each time? So, how do you write the equation of a linear line? Okay, y equals mx plus b. And what is the change going to be? What is the slope? 4. Because it's going up by 4 each time. So I can put it 4n. Now, if I plug in 1, what am I supposed to get? 3. So what do I have to do? Minus 1. Now we can test this. If I plug in 3, what am I supposed to get? Supposed to get 11, so I plug in 4 times 3 minus 1. Do I get my 11? Yeah. If I plug in 7, I should get 27. So 4 times 7 is 28. Minus 1, 27. So some of it is, can we recognize the equation that's being used? How about one a bit more complicated? 3 over, let's say, 2 plus 3 over 4 plus 3 over 6 plus 3 over 8. So what do you see? Okay, so n equals 1. What's the last one going to be? 4. Is this linear? So 3 halves, 3 fourths, 3 sixths, 3 eighths. Is it approaching some number in the long run? So is this divergent or convergent? It's convergent if we kept going with the pattern, which means it's not linear. However, is part of it linear? Which part? Okay, the what? Yeah, the denominator. So we know what's going to be on top, right? So what goes up here? 3. Because there was a 3 every time. How would you put a rule for the bottom? What? 2n. So if I plug in 1, 2 times 1 is 2. Plug in 2, 2 times 2 is 4, and so on. Does everybody follow what we've got so far? Any questions?